Hey everybody, welcome back. Chem 104 lecture, Chapter 7, Part 2. If you're like, wait a minute, what you mean Part 2? There's a Part 1, you should watch it. It's sort of related, but sort of not. It's all part of Chapter 7, all part of chemical reactions and quantities, but right now, we're getting into the quantities part. So Chapter 7, Part 1, qualitative, types of chemical reactions, balancing. Parts 2 and 3, quantitative, and they are related. So in this part, we're going to build the skills that we need to do the more complicated problems coming up in Chapter 7, Part 3. So go through this one slow if you are not a fan of math or math is not a fan of you. It is not bad, but you need to have a process. So get out the color pencils, the markers, highlighters, whatever it is that makes you happy and helps you keep your math organized. Because the biggest problem that I see with students doing chemistry is that they aren't organized. Their work is all over the place if it even exists. With these types of problems, you want to take your time. Make sure you write out all of your units and you make sure all of your conversions are right because we're going back to conversion factors. So just get ready. It won't be bad, I promise. If you just give it the time it deserves and slow down just a little bit when you're doing your homework. Give it a little bit more time. Give it an extra 15 minutes and see what you can do with that. Here we go. We're going to start with the mole, defining the mole and using it in some simple calculations. We'll start by talking about Avogadro. He was an Italian physicist, did a lot of stuff. Part of that stuff was coming up with this unit, the mole. Okay. Avogadro's number says that a mole contains 6.02 times 10 to the 23rd items. Those items could be atoms, molecules, ions. Doesn't matter. 6.02 times 10 to the 23rd, that is a lot of zeros. You don't want to have to write that out. Make sure that you are comfortable with scientific notation. If you're not, you need to refresh yourself with Chapter 1. We can use Avogadro's number as a conversion factor, which means that we can write an equality as well. 1 mole is equal to Avogadro's number, which is 6.02 times 10 to the 23rd particles. The conversion factors, which look like fractions, you're going to take the 1 mole and 6.02 times 10 to the 23rd and write a fraction. Then you write the reciprocal. And there's your conversion factors. You always have 2 conversion factors for every equality. And the equality, just so you don't get confused, always has an equal sign. We're going to be using this equality quite a lot. So how do you use it? Well, you can use Avogadro's number to convert moles to molecules. How many carbon dioxide molecules are in 0.500 moles of carbon dioxide? I always like to rephrase the question. We have moles of carbon dioxide, and we want to get to molecules. Don't confuse yourself by abbreviating molecules. Write out the word molecules. Moles, I abbreviate MOL. You'll see that in other chemistry textbooks. This textbook doesn't really do it, but I do, because I like to write less. So this is our question. What we know is the equality 1 mole of carbon dioxide is equal to Avogadro's number of molecules, 6.02 times 10 to the 23rd molecules. That's the equality. Then we have to write our conversion factors. You put one number on top, the other number on the bottom. Then you write the reciprocal. You flip it upside down. Now we have to decide which one of these we want to use. Starting with 0.500 moles of carbon dioxide, we need to cancel out moles and end up with molecules. Moles of carbon dioxide is currently in the numerator. To cancel it out, we need the conversion factor with moles in the denominator, or the bottom. So we're going to use this one, the second one. Do the unit analysis. Make sure that moles is in the top and the bottom so that you can cancel it. That's the only way that you can get rid of moles of carbon dioxide and end up with molecules. When you multiply it out, you're going to use your scientific calculator and enter 0.5 times 6.02 times 10 to the 23rd. So make sure you remember how to enter scientific notation into your calculator. You should get 3.01 times 10 to the 23rd molecules of carbon dioxide. Don't forget units. Also, don't forget sig figs. So conversion factors, equalities, sig figs, scientific notation, all the things that I promised would reappear, here they are. And they're here to stay. So if you need a review of those things, go back to chapter 1, go back to chapter 2. That's where we did scientific notation, conversion factors and equalities, conversions. All of those things are still valid here. Time for a learning check. As always, try it on your own. See how you do. Then join me. The number of moles of sulfur in 1.8 times 10 to the 24 atoms of sulfur is, so that means our question is, if I've got this many atoms, how many moles do I have? The relationship is still the same. Avogadro's number of atoms is equal to 1 mole. Let's write our conversion factor. We have atoms in the numerator. So that means atoms needs to go in the denominator to cancel. So we're going to write Avogadro's number in the denominator. That leaves moles to go on the top. You're going to be taking the 1.8 times 10 to the 24 and dividing it by 6.02 times 10 to the 23rd. Your calculator will tell you 2.99. But look at our sig figs. We've got 2 sig figs in 1.8 times 10 to the 24. With 2 sig figs, we write that as 3.0, and our units were in moles. The answer should be letter B. We can talk about chemical compounds and how many moles of elements are within that compound. Let's say that we have aspirin. Hopefully the class doesn't give you a headache, or at least maybe I don't. The material, I'll allow it. Chemistry can be a lot sometimes. But hopefully I don't give you a headache. But if I do, that's all right. There's aspirin. Let's represent aspirin as a whole circle. Okay? That's 1 mole of aspirin. Aspirin is made up of carbon, hydrogen, and oxygen. C9H8O4. The number of atoms in one molecule would be 9 atoms of carbon, 8 of hydrogen, and 4 of oxygen. But what this also means is that I can split up my 1 mole of aspirin pie into carbon, hydrogen, and oxygen. And instead of saying atoms, I can say 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. That is what 1 mole of aspirin is made of. We can break it down into the smaller parts. The subscripts in the formula show the relationship of both the number of atoms in the formula and the number of moles in each element in one compound. So that's what we just showed on the other slide. This is another way to show that. Atoms versus moles. But why do we care about that? We care about that because we can use that information about the compound to write conversion factors. So for 1 mole of aspirin, we have a lot of possible conversion factors. In every 1 mole of aspirin, we have 9 moles of carbon. We can also write the reciprocal of that. And that talks about the relationship. If I have 1 mole of aspirin, I have 9 moles of carbon. If I have 1 mole of aspirin, I also have 8 moles of hydrogen. We can also talk about the oxygen. There's 4 moles of oxygen in 1 mole of aspirin. We can write the reciprocals for both of these as well. These conversion factors can help us do calculations to figure out how many atoms or of carbon, let's say, are in a certain amount of aspirin. Like this question. How many atoms of carbon are in 0.150 moles of aspirin? And the chemical formula is given, C9H8O4. The first thing I always do is rewrite the question. We've got some moles of aspirin. We have to figure out the number of atoms of carbon. We can't just jump right there, because we have to go from moles of aspirin to atoms of carbon. Not moles of carbon, atoms. So we've actually got to do 2 calculations, which we can string together. The first one, we're going to take our moles of aspirin and convert that to moles of carbon. We can use one of our conversion factors that we wrote on the previous slide to do that. But the question isn't asking about moles. It's asking about atoms. And the link between moles and atoms is Avogadro's number. So the moles of carbon we can convert to atoms using Avogadro's number. Let's start with part 1, moles of aspirin to moles of carbon. We've got to write a conversion factor. That's the carbon. That's what we care about. If we have 1 mole of aspirin, we have 9 moles of carbon. Then we write the reciprocal. For the second part, where we're going from moles to atoms, we need to use Avogadro's number. If I have 1 mole of carbon, I have 6.02 times 10 to the 23rd atoms of carbon. And of course, the reciprocal. Now we can put our equation together and choose which conversion factors will get us from moles of aspirin all the way to atoms of carbon. I like to write my plan of what units I should be getting to above my equation. Starting with moles of aspirin, After our first conversion factor, we should be at moles of carbon. And after the second one, we should be at atoms. To get rid of moles of aspirin from the numerator, we need the unit, or the conversion factor. Unit factor is what other books call it. I've got so much terminology in my brain, sometimes it hurts. We need to choose the conversion factor with moles of aspirin in the denominator. Second part. We're trying to go from moles of carbon to atoms of carbon. Currently, moles of carbon is in the numerator. We need that in the denominator to get rid of it. Now we do our check with the units to make sure we're going to end up with what we want. You have to have a unit in the numerator and the denominator, the top and the bottom, in order for it to cancel. We get rid of moles of aspirin and we're left with moles of carbon, which is the first step in our plan. Then we get rid of those moles of carbon and we're left with atoms of carbon. That checks out. When you're doing this in your calculator, you're going to take the 0.15, multiply by 9, and then multiply again by Avogadro's number. With sig figs, which we need 3 sig figs here, you should get 8.13 times 10 to the 23rd atoms of carbon. We'll do plenty of practice of these problems and all the other ones in this part of Chapter 7. So don't worry, just come to class. The next concept that we're going to cover is molar mass. And I'll remind you again, we're building these concepts so that we can string them all together for the third part of Chapter 7. We're not just doing this in abstract, we're doing it so that we can put all of these together as building blocks to do more complicated problems. Molar mass. If we're given the chemical formula of a substance, we can calculate its molar mass. Molar mass is just the quantity in grams that equals the atomic mass of that element. Let's talk about it. If I have 1 mole of an element, then the molar mass for that element is the atomic mass expressed in grams. If you look at the periodic table, for carbon, you'll see 12.01. That's the atomic mass. It's measured in atomic mass units. Express that mass in grams, and you now have the molar mass of carbon. 1 mole is equal to 12.01 grams. That's an equality. And this is a molar mass. Same with lithium. 6.941 atomic mass units. That's the atomic mass. Instead of AMU, we put grams, and now it's a molar mass. It is also an equality. So we've got 1 mole of carbon over 12.01 grams of carbon. You can also have the reciprocal. And the same for lithium. We can calculate the molar mass of more complicated compounds simply by adding together the molar masses of each of the elements involved. Let's calculate the molar mass for lithium carbonate, which is used to treat bipolar disorder. The elements that we have here are lithium, carbon, and oxygen. We know from the periodic table there's 6.941 grams of lithium for every 1 mole of lithium, and that in our formula here, we've got 2 moles. Remember these subscripts. We've got 2 moles here. When you do that multiplication, you get 13.882 grams. So that's how much lithium is in 1 mole of lithium carbonate. We've got to do the same thing for the others. There's our carbon. Now, the periodic table in your textbook may have 16.00 as the atomic mass for oxygen. If you use 15.999, which is on the periodic table that I uploaded to Blackboard, you'll still get the same answer. So this is a list of the masses for each of the elements in lithium carbonate. We have to add them up as our last step. The rules apply that we learned for adding sig figs here. I draw my dotted line, which shows me my last retained digit and what digit I'm going to use to round. You can still use your calculator here, but make sure that you know where you're rounding. This second 8 is going to be my last retained digit. I'm going to look at the 9 to see if I round up or stay the same. 9 is definitely 5 or more, so I'm going to round up. This is our final answer. And remember, that's equal to the mass of 1 mole of lithium carbonate. Now that we know how to calculate a molar mass, we can use the molar mass to do calculations. So in this section, we're going to take the mass and convert to moles, and vice versa. We know that the molar mass we can write as conversion factors. You've got grams of the substance for 1 mole. So if I told you that 1 mole of methane which is CH4, is equal to 16.05 grams, you should be able to write these conversion factors. There's one. Then you write the reciprocal. So that's a quick review. But how do we use that molar mass? Let's practice. A box of table salt, NaCl, contains 737 grams of sodium chloride. How many moles of sodium chloride are in the box? What is our question? Well, we've got all this table salt. You know you got a box of Morton's. Let's just be honest. That box of Morton's salt is 737 grams. Because you're in a chemistry class, you're going to try to figure out how many moles that is. What information do we know? Well, we can calculate the molar mass of sodium chloride. And if we have that molar mass, then we can use the molar mass, which I abbreviate MM, as a conversion factor. And we can go from mass to moles. Now, I'm not going to show you how I came up with the molar mass of sodium chloride. You're going to look up sodium, you're going to look up chlorine, you're going to add them together. When you do that, this is what you get. 58.443 grams are in 1 mole of sodium chloride. That's our molar mass. Now we can use this to go from our grams to moles. We're starting with grams in the numerator. To get rid of grams, we need to have grams in the denominator. So that mass goes in the bottom. On top, we put the 1 mole. The grams cancel. We're left with moles. Great. Now we need to consider sig figs. We've got 3 sig figs in the mass that we were given. We've got 5 sig figs in the molar mass. Since we're doing multiplication and division, we go with the fewest number of sig figs, which is going to be 3 significant figures. That means our final answer is 12.6 moles of sodium chloride. Here is a map of mass, moles, and particles. This shows you how you can convert from one to the other to the other. Make sure that you understand how to do that, because that's where we're headed. We can start with the mass of an element and convert it to moles. And from there, we can go to moles of atoms, moles of a compound. We can go a bunch of different places. But understand how you can use molar mass and Avogadro's number to go back and forth from grams to atoms or moles. That's it for this part. Short and sweet. We were building some skills. Come back for part 3.